Good morning, Doctor, and greetings, ladies and gentlemen. The topic of our presentation is Sustainable Biofuel Production from Waste Sources. This presentation is prepared by Group 5 with members Zhang Taining and Nu Fatiha. Our presentation will cover background of problems, existing solutions, gaps in current technologies, and the new strategy proposal for sustainable biofuel production from resources. Background of problems. In terms of biofuel, the demand for fossil fuels keeps increasing due to our society's development. Since the primary energy sources nowadays have a limited amount and unrenewable characteristics, it is essential to find and investigate other available resources. Another problem caused by fossil fuel is carbon dioxide emission, which leads to chain effects on the environment, such as global warming, glacier melting, sea level rise, and etc. Biofuel is one of the most reliable energy sources to replace fossil fuels. Biofuel can be generated from plant waste, animal waste, food waste, microbes, and etc. In our presentation, we will focus on biofuel production from food waste, particularly bioproduction from anaerobic digestion of food waste. In terms of food waste is one municipal solid waste with great potential for biofuel production through biorefineries. According to the United Nations Environment Programme's 2021, the world produces 931 million tons of food waste yearly. 17% of global food production may go wasted, and 61% of this waste coming from households, 26% from food services, and 13% from retail. The amount of food waste is increased by population growth. Most of the food waste is not adequately treated. For example, in Egypt, a large number of food waste is either burned or dumped in the junkyard, which causes health and environmental problems. Another example, in the US, 95% of food waste generated by consumers and retailers ended up in landfills, becoming a major source of anthropogenic methane emission. Hence, recycling food waste for biofuel production will help with the energy crisis and the environmental problems. Normally, the biorefinery of food waste into valuable products is divided into three major categories. First, the application of enzymes or microbes to convert food waste into biofuel is known as biological pathway. Second is the thermochemical pathway using chemical solvents with elevated temperatures to recycle food waste. Last, food, food waste valorization under the chemical pathway with the help of chemical solvent as a catalyst.
Existing solution. First is they divided into three: biological, chemical, and thermochemical. First, biological. The first technology is anaerobic digestion. It used for the generation of methane from organic matter in the absence of oxygen. The biological process include hydrolysis, acidogenesis, acetogenesis, and methanogenesis. The first step is hydrolysis, where substrates are converted into soluble molecules. Extracellular enzymes called hydrolyses are used to conduct hydrolysis reaction. Hydrolysis can include esterase, glycosidase, and peptidase. This step transforms carbohydrate into sugar and convert lipid and protein to long-chain fatty acid and amino acid. In the second step, fermentative bacteria transform soluble molecule formed at the hydrolysis stage into volatile fatty acid, lactic alcohol, and CO2. The main products in this step are acetic acid, propionic acid, and ethanol. In the acetogenesis step, acetogenic bacteria oxidize urea and alcohol into acetic acid and hydrogen. Bacteria that form the acetate by using butyrates and propionates respectively are known as Synthrophotobacter balinoi and Smithella punica, Maculum stenici, Clostridium aceticum is another microorganism that develop hydrogen and carbon dioxide acetate. The last step is called methanogenesis. Methanogenesis where CH4 Methane and carbon dioxide are derived from acetogenesis product by methanogenic bacteria. Second, second technology in biological is fermentations. It produces ethanol and mainly includes five main steps: feedstock preparation, pretreatment, release of free fermentable sugar, fermentation, and purification. Pretreatment step use of acid, alkali, thermal, and enzymatic process to increase the digestibility of the cellulose component of the food waste. Fermenting organisms such as Saccharomyces cerevisiae and also Xymonas mobilis. Is chemical solutions. Process called is transesterification. In food waste recycling to biodiesel. Chemical reaction between two immiscible phases, one being the triglycerides, lipid available in food waste, and animal fat and also vegetable oil, and the other is alcohol, ethanol or methanol. The process is preceded by a pre-treatment step, hydrolysis, to extract the lipid from the food waste. The reaction involves the exchange of an organic group R in the lipid ester with R organic group available in the alcohol. This reaction also requires heat, stirring, and acid-base catalyst that will eventually result in the synthesis of the biodiesel. Food waste biodiesel is very similar to the petroleum diesel in terms of density and viscosity. Only 10% left in high heating value but relatively high in ignition point. Third is type of thermochemical technology. First is a pyrolysis. Pyrolysis is a thermochemical process, the conversion of clean matter to fuel, chemical, and biochar. A high temperature, around 200 degrees Celsius, and an inert environment is required for the reaction to take place in a small enclosed space, the reactor. During pyrolysis, the moisture is first removed from the organic matter, then followed by thermal decomposition of the organic matters to produce a pyrolysis gas, which upon condensation produces a permanent gas and a pyrolysis liquid, commonly referred to as tar or bio-oil. The bio-oil has the highest energy content compared to the other pyrolysis products as gas and biochar, hence it has high potential as a liquid fuel in energy applications. The pyrolysis bio-oil can also be utilized as a source of chemical depending on its characteristics such as water fractions, viscosity, density, chemical composition, and pH. The main advantage of the pyrolysis process, particularly for food waste conversions, is that minimum pretreatment is required if the correct type of reactor is used. Pyrolysis also differs from the other thermotreatment technology as of gasification in that it takes place in the absence or limited oxygen environment. Second method for thermochemical is gasification. Gasification is similar to pyrolysis in that they both use heat to break down organic matter into hydrocarbon. However, unlike pyrolysis, gasification happens when it is partially oxidized at a higher temperature between 800 and 1200 degrees Celsius, and mainly it produces gas, and a particulate solid product. Commonly, air is used as the gasifier agent. However, pure oxygen and steam can also be used to improve the quality of the product gas. The gas is mainly comprised of carbon dioxide, monoxide, methane, and a very small fraction hydrogen and a very small fraction of tar. There are a variety of potential applications of the gasification particulate, such as biodiesel production and a catalyst for tar catalyst cracking. The reactors used for gasification are mainly fixed and fluidized bed reactors, which are very similar to those that used for pyrolysis. Gaps in the current technology, which is the technology anaerobic digestions. Biogas has harmful and unwanted substances like hydrogen sulfide, water organic compound, and ammonia. Hydrogen sulfide and ammonia are harmfully and highly corrosive, causing harm to combined heat and power unit and metal bulk. The presence of hydrogen sulfide affects the quantity and the quality of the generated biogas, as well as it emits harmful emission and corrode the biogas purification. Since the biogas generated by the AD contains impurity, it typically needs the preventative treatment to boost the methane yields and the post-treatment to eliminate hydrogen sulfide. These processes are energy intensive and as well as expensive. AD the high cost and strict startup conditions, and in AD, high amount of lipid may have a negative effect as a limiting factor in the methane generation, as methane production was strongly positively correlated with the lipid reductions in the food waste. As in one study, it mentions that uh, the ratio of the amount of lipid in the food waste must not be less than the 5.5%. The threshold of the food waste.
New strategy proposal. Here we propose some potential strategies based on the gaps mentioned by my friend Fatiha just now. The removal of unwanted gaseous substances can be achieved by using iron biochar combo. Biochar derived from waste has been increasingly considered a potential green adsorbent due to its significant ability and affordable production costs. Several studies showed effective removal of gaseous substances from biogas using biochar, which includes hydrogen sulfide, carbon dioxide, and ammonia. It is also capable of removing volatile organic compounds. The reason why combining biochar with iron is to increase the efficacy of removing hydrogen sulfide. Due to hydrogen sulfide is incredibly responsive to different types of metals, and hydrogen sulfide produced during anaerobic digestion causes problems, such as corrosion of generators, which produce biogas, and low gas quality if the content of hydrogen sulfide is too high. This strategy aims to elevate the removal process of harmful and unwanted substances to increase the purity of biogas. The pre-treatment and post-treatment of biogas production. It is inevitable to avoid or skip pre-treatment and post-treatment of biogas production. Why? Because the complex composition of food waste, we need pretreatment such as elevated temperature or pressure in order to obtain better hydrolysis and provide a more homogeneous crop for feeding aerobic digestion. And of course, post-treatment to purify biogas. However, we can still optimize or integrate these treatments. For example, we can use a strategy which integrate auto-generative high pressure and hydrogen injection because using the auto-generative high pressure approach alone will decrease the production yield when pressure reaches certain point. But with hydrogen injection, the production yield will not decrease at that certain point. High cost, strict startup condition. By building a model of production and consumption, we can integrate the concept of circular economy, which links all the characteristics such as different treatment units involved in recovering valuable components and the equipment associated with its transformation, energy demand, the number of resources involved, transportation cost, price of products, optimization of product yield, integration of different approaches, recycling digested materials. With these characteristics linked all together in order to achieve more profit with less cost. The high amount of lipid. In the case of lipid-rich food waste, we can integrate transesterification and aerobic digestion. Transesterification can reduce the lipid content to produce biodiesel, and the less lipid content will guarantee the high production yield of biogas from aerobic digestion. These are the references for our presentation. Thank you. That's all from us.